board. Okay. So first thing I want to do is talk a little about wall framing. So let's go ahead and get to the slideshow. So what we're going to be doing is sizing headers. So the header is the part here that goes over an opening. So you can have a door header over a door or a window header opening a window. Um, when we work on this in Forte, there's a stud that runs all the way up along the end of the header, but that doesn't actually hold up the header. The ones that actually hold up the header are these, and I call them shoulder studs. There's probably another name, which I'll show you on the PowerPoint here. But the bigger that your span is, the code might require you to have two or maybe even sometimes more studs holding up that header. The other thing we're going to talk about is lateral bracing. So this has got OSB on the outside, and that provides resistance for the house wanting to tip over. So like if there's a wind blowing on this wall to the left where it says wall framing, that load will get resisted by the ply or the OSB on the wall going in the 90-degree direction, because that will be nailed to the studs and that will try to keep the house from tipping over. What happens if the wind's blowing towards us from like the forest out there is that this wall has to have lateral bracing. Now, the reason I like this photo is you can tell this is a townhouse, right? Where it's like a row house where there's, if it was the outside wall, they would put the OSB on it, but it's not. It's got to be a firewall probably between the units. So they've got a layer of gypsum board running between it. But the reason I like this is you'll notice there's a metal brace here and there's a diagonal metal brace there. And those are providing the lateral stability in that direction. Those metal braces are like notched into the studs with like a saw curve. You can kind of even see what there, and then they're nailed into each stud. So by putting that diagonal in there, that stiffens that wall to keep it from wanting to tip over this way if the wind's blowing in towards us in the picture. So now this is showing a header supporting a floor load. I'm going to give you an assignment where the header is supporting the roof load. But it's the same concept with the headers. Okay, so let's get going here. Now we're going to do a little bit of a history lesson. So before World War II, they had what was called balloon frame. And remember, they had this old growth timber that was nice and tall and straight. So they could get a two-story house with one stud out of these big old trees that was nice and straight that went all the way from the foundation wall up to the second floor roof. And what they would do is, the reason that that was good is that the plaster they used was a lot more prone to cracking than drywall was. And wood shrinks less if it's in the direction that it grew up in the forest, up and down. It shrinks less in that vertical dimension, but it shrinks a lot when you lay it on its side. So if you look at this, there's a double top plate there holding up the roof, and then there's plates at the bottom, but there aren't a lot of wood laying sideways on that wall. It's just one stud all the way up. So it was much more resistant to cracking the plaster. The problem is that, were you a firefighter? Okay, so you've got one stud all the way up and it's got boards on one side and plaster and lath on the other. If a fire got into that wall, there was nothing to keep it from running up like a chimney and burning the whole house down very fast. So what they had to do is they had to put fire stops in between the floors so that if the fire got into this wall, that fire stop stopped it. It took a long time to burn through that 2x4 to get up into the wall. Because if you ever looked at a chimney, you know, once you get into that stud cavity, it's like a chimney. The hot air rises and it will instantly go up, and then your whole house burns, your first and second floor. So the problem, apart from the fire stopping, was it required very skilled carpenters to do it, because you had to notch in all these, like this rib end that's holding up the joist had to be notched in. And I'll show you this in a isometric on the next page. So where we're at now is what's called platform frame, where we build our floor, we build our walls on it and tip them up. We build our floor on for the second floor, we build our walls on them and tip it up. So look at all the wood that's laying on its side on the height of that wall. 33 inches when you do all the math, all the wood that's laying on its side versus 6 inches on the other way. So that the only reason we can get away from that is drywall is a lot more, gypsum board is a lot more flexible and less prone to cracking than the old school plaster was. So that's why we can put, and there's a lot of advantages as far as less skilled lumber, it's safer, it's easier to, less skilled carpentry, and it's easier to build and it's safer to build on because you're building off of these platforms. Okay, so here's an example of how they actually used to frame these things. Is so you can see that that ribbon was let in, and this was all done without power tools. So they're using saws and chisels and all that. So they're notching this in, and it was labor intensive and it required skilled craftspeople. They didn't have plywood back in the day either, so they had to take one by I think it was 1 by typically, maybe 2 by solid wood planks, and they laid them diagonally on the floor. So you're never going to build a building like this, but you might end up remodeling or adding to a building like this. Have you ended up remodeling or adding to balloon framing? Did you ever work in remodelings? So it's not going to be your new construction. So what we do today is called platform framing. It was used to also be called West Coast or California framing because that's where it was invented. We needed to build a lot of houses for all the servicemen coming back from World War II. It was constructed one floor at a time on a platform, so went faster. It was safer for the workers. And it automatically had huge fire stops between the floor, right? Because now I've got to burn through a double top plate to get up to the floor, to get up to the stud. So it was much more fire resistant without putting a lot of extra fire blocking. Now, we talked before, it's less dimensionally stable than a balloon frame, but with drywall, we didn't care. Back in the old day, they used to use cement, plaster, stucco on the outside. That was also very prone to cracking. Now we use, it's called EIFS, exterior insulation finish system. It's much more flexible and not prone to cracking. So if you're in a high wind area, like a hurricane area or a seismic area, they need to put steel connectors to tie the floors together because they're broken now. They're not one stud all the way up. It's like a stud sitting on top of a stud. So we need to tie them together if we're in a high wind area or in an earthquake area. So you probably heard me going on about 8-foot pre-cut stud walls. So when we're working on houses, we need to know the way they actually build them because they don't build their stud walls 8 feet high. So if you measure your ceiling, it'll be a little bit more than 8 feet off the floor. That's because 8-foot pre-cut walls got to be that dimension for a reason. So when you take the 92 5/8 8-foot pre-cut studs and you add the 4.5 inches for the double top plate and the single bottom plate, you end up with 8 foot 1 1/8. So then what you typically do is when you put your drywall in, you typically put 5/8 on the ceiling, and that goes first. So they call it rocking the lid. So you put your 5/8 inch drywall on, then you put a 4-foot sheet of, they typically put the sheets, now this shows the drywall one sheet going up and down. In my experience, they typically lay it sideways. They put their 4-foot sheet up against the top, and then they put their next 4-foot sheet up against the next one. That leaves a 1/2 inch gap at the floor. You need to have that gap because if that floor is a little bit uneven, and plus putting the sheet of drywall, it can't be a perfectly tight fit. So there always needs to be that gap on the bottom. And they make this cute little jack. I don't have a picture of it, but this little jack, you just step on it and it raises the sheet of the drywall up tight to that upper sheet. So you don't have to like bend down and kind of hold it up with your finger stuck in that 1/2 inch gap. So that gap is always covered by the baseboard. So when you go in a house, like this has got a vinyl baseboard, but if you go in a house, they typically put a wood baseboard on it that covers that gap there. Now, they do also make 9-foot pre-cut walls, So that's just ends up with a 9-foot 1 1/8 wall. Now, how does that work? Well, they make 4-foot 6-inch wide sheets of drywall, so it works the same exact way. You still have that 1/2 inch gap at the bottom. So 8-foot 1 1/8, 9-foot 1 1/8. We don't ever want to make the carpenters have to cut studs individually. We want to let them use the pre-cuts if it's at all possible. Okay, so did Josh talk to you all about advanced framing at all? Okay. Um, did he? I saw Audra nodded her head. Yes, nobody else nodded their head. Did Josh talk about advanced framing? Yes, okay, now I see more nods. Okay, so advanced framing uses less lumber and reduces thermal bridges. You typically on advanced framing, you do your outside stud walls 24 inches on center and not 16. It reduces corner studs, jack studs, which are the ones that I call shoulder studs that hold up the header, and cripple studs, which are the studs above the header. So this is a little SketchUp version of advanced framing. So let's see if this video still works here.
With 24-inch layout. Advanced framing begins with 24-inch layout. It's usually a good idea to stack the framing because it...
Okay, now he's talking about stacking the framing. Advanced framing, if you're being pure about it, uses a single top plate, not a double top plate, because they're trying to absolutely reduce the amount of lumber. So this one's kind of a hybrid where they showed you what a double top plate looks like here, but this is a single top plate. If you're doing like pure advanced framing, you have a single top plate, and then they do a metal connector to tie it together where it butts up against the next one. Now, the problem with pure advanced framing is your trusses have to line up on your floor joists, which have to line up with your stud below it, because that single top plate is not strong enough if your trusses don't fall directly on a truss. So I would never recommend somebody use pure advanced framing with a single top plate because it's too complicated to get all that framing to line up. If you're totally into energy efficiency, there might be this very, very marginal benefit, but all the hassle you have to go around to line up your floor joists on your levels and line up your trusses and make sure all the studs line up and where you put the openings, it's not worth it to me.
Makes the plywood layout more predictable. But if you're using single top plates instead of double plates, transferring the load is required because of science and the building code. But a lot of framers stick to double top plates for a more mundane reason, so the drywall fits.
So I'm just going to pause there. When he says so the drywall fits, remember what I just told you about the pre-cut studs? If you get rid of that double top plate, now your pre-cut studs won't work with the drywall. You have to trim all the drywall and your ceilings aren't at 8 feet, or you've got to cut all the studs individually to length to make the walls 8-foot 1 1/8. So to my mind, double top plates absolutely make sense both for strength and the code, ease of framing, and getting your drywall to work. It's not worth it to get rid of the double top plate, in my opinion. Okay, let's go.
There are a lot of options for improving energy performance of headers, from those that support a second floor and a roof to those that support nothing at all. If the header supports nothing at all, omit the header. In larger openings with omitted headers, it's worth doubling up the sill and head plates. For large openings that do need structural headers, you can make an insulation sandwich with 2 LVLs and a 2-inch slab of foam or rock wool. This fits perfectly into a 2x6 wall. An option for point loads over large openings is to recess an extra layer of end joist into the floor system above the opening. Recessing an extra ply into the rim joist can eliminate the need for headers in the wall, but you'll have to cut a few of the floor joists shorter. For joists that stack over studs, make sure there's enough bearing on the wall. For joists over openings, add joist hangers. For structural headers carrying very little weight, look it up in a load chart and then size it right. corners afford opportunities for improvement too. One stud at the end of each wall makes the maximum amount of space for wall insulation and is structurally sound. You may have to convince your drywall contractor to float the corners, but you should get far fewer cracks and corners from wood movement. Inside the house, there are a lot of ways to do partition walls, and here's 2 of them. Use ladder blocking between studs rather than boxing out a post as a wall backing. Ladder blocking eats up scraps and makes more room for continuous insulation. An even better way is to gap the wall so that the drywall can be slid behind the joint for a continuous air barrier. This also allows full-depth insulation in the stud cavity. The top of the wall is anchored with a steel connector or a block of 2x4. One more boost that framers can add at the design stage is to suggest using raised heel trusses. They extend up significantly higher before the roof pitch begins, which allows a thick blanket of insulation atop the outside walls.
So I know, Josh, I see your sketches there. He must have been talking to you about heel heights and insulation. Now, real world. When we work with Habitat, they typically say, we're going to do 2 2x12 headers and size the worst case to make sure 2 2x12s works. They do 2 2x12s everywhere. Okay. That's the way it typically works in the real world, in my experience. You just say, yeah, we're going to use 2 2x12s for headers. And if we have a big one, we'll size it. Maybe you have to use an LVL there. They don't size each individual header and say, oh, we can get by with a 2 2x6 header. Even though structurally you could do it, I'm assuming, again, not being a carpenter, but I'm just assuming it's like, if I got 2 2x12s and all my jack studs are the same height, I don't have to figure out which one goes where. And it's not worth it for most people to dink around and size. You don't want to have to size all the headers individually to get the absolute bare minimum wood in there. That's the way it typically works in my experience. So I know they said in this one, if you're totally concerned about energy, yeah, you can get rid of headers if they don't take a lot of load or any load, or you can make them very small if they take light loads. But that's not the way it works in the real world, in my experience. You just do the worst case, make sure the 2 2x12s work. If it doesn't work, like for a really long header for like a garage door, then you do LVLs. Now, that's the way Habitat rolls. Now, we have a new Habitat construction coordinator that comes in to talk to us next class, and we'll see. We're going to ask his opinion on how he wants us to build the house. So let's go back into my PowerPoint here. So as I mentioned before, I think that advanced framing, if I ever was using it, I would use the double top plate so all my framing didn't have to line up. I just want to show you a quick other video with advanced framing, and this is from the plywood or the OSB sheathing people, that shows they're using advanced framing techniques, but with a double top plate.
To improve energy efficiency. Careful consideration of the load path often allows for
Why did it start in the middle? Okay, let's get going here.
Hi, I'm Randy Melvin. We're here at the site of a new home in Lockport, Illinois. The system we're highlighting today is 2x6 24-inch on-center advanced framing. Using familiar building materials and methods, advanced framing maximizes material usage and energy efficiency. Advanced framing benefits both builder and homeowner. For the builder, 2x6 advanced framing is a cost-effective way to meet requirements of the energy codes and above-code programs like Energy Star. For the homeowner, advanced framing results in a comfortable residence with superior energy efficiency. And advanced framing is a green building strategy that uses a renewable resource with maximum economy for environmental sustainability. Let's take a closer look at how advanced framing techniques are implemented in this home. There are a variety of advanced framing techniques that can be incorporated as a whole package or individually. One technique that can be used with 2x6 studs is wider stud spacing. This house uses 2x6 studs spaced 24-inch on center instead of 2x4 spaced at 16 inches. This reduces the number of pieces to install while providing increased space for more insulation. Building with 2x6 studs spaced 24-inch on center is an easy adjustment. Builders don't need new or specialized tools. The increased depth and width in the wall cavities leaves much more room for insulation while maintaining excellent structural integrity, thanks to continuous sheathing with wood structural panels. In this home, the technique results in a strong wall that is very energy efficient. Insulated corners are another advanced framing technique that we used. Conventional 3-stud corners isolate an uninsulated space in the wall, which is not permitted with today's energy codes. Advanced framing maximizes corner insulation with methods like California corners or 2-stud corners that use drywall clips or more commonly ladder blocking. The insulated corners help optimize the energy efficiency of the entire wall. A California corner, also known as an insulated 3-stud corner, orients the studs so that the entire corner space can be insulated. The insulated 3-stud corner opens up more insulation space and allows for easy drywall attachment. Another advanced framing technique, ladder blocking, which is used at the intersection of interior walls. Ladder blocking eliminates the inaccessible.
I'm going to pause. He's going to show you two different kinds of ladder blocking. So this one, the ladder is set up so that the stud goes the full depth of the wall. He's going to show you another one where you turn that thing vertically, and then that gives you continuous insulation. Because like this horizontal piece here is a thermal bridge through your insulation, and there's really no reason why. You can put them vertically and still have a. So I'm going to show you that. Keep an eye on the next one they show you.
Uninsulated cavities that were typical with construction methods of the past.
See,
using ladder blocking at junctions
and
between interior and exterior walls leaves an open, accessible area for easy installation of insulation. Note that when ladder blocking is used flatwise, it provides a larger nailing area for drywall installers in addition to space for a continuous layer of insulation uninterrupted by conventional blocking. Headers are sometimes overlooked as an area where insulation can be added to improve energy efficiency. Careful consideration of the load path often allows for insulated headers like these engineered wood headers. When design loads do not require full wall thickness headers, the amount of space occupied by structural members above windows and doors can often be reduced by at least one ply to provide space for insulation. The importance of wood wall sheathing in an advanced frame home cannot be overlooked. In addition to being part of wall bracing and shear walls and other structural code requirements, the sheathing also serves as a code-compliant nail base for siding and trim at corners, as well as with 24-inch on-center framing when the siding installation calls for fasteners to be spaced every 16 inches on center. Continuous wood structural panel wall sheathing is also a recognized air barrier material that can be used as part of an exterior air barrier system when joints and penetrations are properly sealed. In this video, we've looked at advanced framing techniques, including 24-inch on-center 2x6 framing, insulated corners and headers, ladder blocking, and structural wood panel sheathing. These building techniques are easy for builders to implement and result in a highly energy efficient home that will give the homeowners a lifetime of comfort and cost efficiency.
So I taught a similar class, maybe it wasn't similar, it was building science and materials to the wood tech program. And I would ask them to watch, there's all kinds of videos on YouTube about the advantages and disadvantages of advanced framing, and then you can read the comments on YouTube, which is half the fun. But I asked them their opinion if they would use advanced framing on houses once they got out. And a lot of them were like, no, less wood means it's less strong. And you know, like if there's a tornado or a strong thunderstorm wind, I just have less studs holding up my house, so I don't feel comfortable doing it. So I think structurally you can run the numbers and it works, but as far as like why aren't all the houses in the world built with advanced framing? I think that there's still a resistance to doing advanced frame. Now, you guys that worked in the field, did you ever do 24-inch on center on the outside? No, because it's buildings are traditional, and people, if it works, people don't want to change it, right? So I wouldn't be adverse to doing 24-inch on center framing, but there's a reason. And I've heard other things like hanging kitchen cabinets on the outside wall. There's a lot of weight going on there. Now I got to put more blocking in there because I got my studs further apart. So both these guys nodded no, that they'd never done it. So it seems from an energy standpoint to make sense. And I guess my point is that if energy gets very expensive, you'll probably see more of it. But if energy doesn't get more expensive, I think it'll be a very slow, in your lifetime, it'll slowly go up to 24 inches on center. Um, so I don't have any, I'm not against it at all. The only thing I'm against is the double top plate, as I probably told you ad nauseum here. Okay, so let's keep going. So I already talked about all that. So let's talk about openings here. So when they talk about the rough opening, that's not actually the same as the size of the actual window. So if you buy a window at Menards and you put your tape measure on it, it'll be 4 foot. But when you make the hole in the wall, you make the hole in the wall like 4 foot 0.5. That hole that you make in the wall is the rough opening. And it can't be exactly the size of the window because your opening might be a little bit off a square, or the window might be a little bit off a square. It's not like made with lasers in a factory where you can make everything the exact same size. So you put the window in there, you can square it in the rough opening, then you use spray foam around the gaps. But it's the window rough opening is not the same as the window unit dimension of the window itself. So let's talk about headers. So the header takes the load and spreads it over the window. It acts like a little beam basically. And it's also called a common stud, but the stud that runs along the outside is called the king stud on this document. And then the little one is called the jack stud, or I call it a shoulder stud, because it kind of makes sense because like the head is supported by your shoulders in some way. That's the way my mind thinks about it. So this would be like one stud. This would be like one shoulder stud or one jack stud is holding up that header. Now the code tells you how many studs you need based on the window opening span. We're going to get into that when we get into Forte. But Forte also will tell you that, it will check to make sure that if you have a super heavy loaded, very short header, you might need to double up the studs, and Forte will tell you that. So then above the header, if the header's down low, they call these cripple studs, these little ones up on top. So here's some more pictures. Here's jack studs, king studs. This is called the sills. They're calling this the trimmer, what I call the shoulder stud, and the other one called the jack stud. So there are different names for all this stuff. So these are showing those wall blockings for like where intersecting walls come in. And so you can see we always have a double top plate and a single bottom plate. Now let's talk a little about insulated headers. I've seen them made all three ways, believe it or not, on site. I've seen them where they make it like an insulation sandwich where you have rigid insulation in the inside and then you have a ply on the inside and the outside. I was told, I used to do that all the time when I was doing houses. Sometimes my structural engineer would tell me that he liked it better when the studs, the header plies were together and nailed together on the outside, because he liked that better because the sheathing got nailed to the header and then the headers got nailed together without any insulation between them. So he thought it made a stronger house. So so there's advantages and disadvantages to all these. The problem with this one works better structurally, but the problem is if you put the foam on the inside and you don't seal the gaps around it, this is solid wood, so it's going to be really cold, right? And so what's going to happen, and if you put the insulation on the inside and you don't seal it, that warm, moist air can go in and condense on that cold interface of the header and get condensation on it. So for building performance, it works better to put your foam on the outside and then nail the two together on the inside. So I don't really know what the right way is as far as nailing the plies together. And again, the videos I've been telling us for advanced framing, they do one ply headers. Again, in the real world where I worked all the time, we never did a one ply header. We always did a doubled up header. You guys are nodding your head. You're both nodding their head. Again, traditionally, you always do a double ply header. So you guys in the field, which way did you typically do an insulated header? Well, a sandwich or the insulation to the inside or the insulation to the outside? Sandwich? You never done an insulated header. Okay. So I've seen it all three ways. So I don't really know if one is better than the other. I do know my engineers told me on some projects that they wanted them nailed together on the outside. But to my way of thinking about it, if I did the sandwich this way, if this one header was taking the load and it started to fail, eventually that other ply would take up the benefit. They didn't have to be nailed together. So I don't think it's really totally critical how you do this. You could probably ask Josh on his class which way he thinks is the best way to do it. It'd be good to get his opinion. Okay, so the other thing we need to worry about on stud walls is that if we just build a stud wall and we don't put anything on it, it's like a house of cards. If the wind blows on enough on one side of the house or the other, those studs, they're rectangles and they'll just rack and tip over. You've probably tried to build a house of cards, right? If you push on it one way, those things have no support. So the OSB or the plywood sheathing on the outside acts as a shear panel. And that's the most common way to keep your house stable in a high wind. The code requires 20 pounds per square foot load coming horizontally, blowing on the face of your house. Okay, so every square foot of your house, somebody's pushing on it 20 pounds, and that wall has to resist that lateral force. So in the old school ways, the way they used to do this is they would do a 1x4 lead-in brace. So again, this was back when carpenters were very highly skilled. They would cut these with their hand saws and chisel these out, and it would fit perfectly. But nobody really does that anymore. If they're going to do this, now if you have foam sheathing, the perfect wall back there with 4 inches of insulation, that foam doesn't do anything for the house tipping over. Okay. The nails will go right through that foam and your house will tip over. Okay. So I started my career in the energy crisis and we used foam sheathing and we had to do, like, say we did 2 inches instead of 4. We would do 1.5 inches at the corner and at certain parts, and then do our 1/2 inch sheathing just to get enough OSB or plywood on there to keep that house from tipping over. You can't do 4 inches foam everywhere without the metal bracing or without putting a wood sheathing on it to stabilize it. The other downside we found by doing all our walls with foam is that if you have a vinyl sided house, people can literally break into your house with a hammer. Bam, 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 walk through the studs and they're into your house. Okay. So when I was starting, energy was very expensive. Everybody was using foam sheathing. Now I see a lot of fully sheeted plywood or OSB houses. So it's kind of gone back from what it was when I started my career. Now, the perfect wall for energy is to have foam sheathing because it's a continuous layer of insulation. It's like a layer of fat on the outside of the structure that keeps the structure warm. So let's keep going here. You've probably all built a bookcase at Walmart and it's ready to fall over until you put this very thin coated plywood on the back and nail it in, and then it stabilizes it because that's acting like a shear panel. So are walls getting taller on houses? Yes, they are. Are windows getting larger? Do people love large windows? Yes, they do. So back in the day, if you look at the old houses from like the 50s and 60s or 40s, there's these tiny little windows, not a lot of windows on a house. Now modern houses are like walls of windows. So they had a problem with these tall walls with all these holes in them that the houses were actually failing in high winds and they were racking and wanting to tip over. So the code requires you to put sheathing on or metal cross bracing to provide enough bracing for lateral stability. So this is showing here that they're going to tell you how many feet on a house you need to have lateral stability or bracing. So here it's saying that I need braced wall at the end. I need a braced wall panel at the corner. Um, on certain conditions, I might need 48 inches from the corner. If I've got a bunch of holes, I need to have my first brace wall panel 10 feet maximum in. I don't teach you the ins and outs of this, basically because to do it right, I'd have to take maybe a week to teach you this. You're going to learn this on your own when you need to in the real world. Um, and the other reason we don't do it is Habitat does not put walls and windows on their house, and they do continuously sheathed walls where we're going to put OSB on everything. So we don't have to worry about this too much. But when you get out into your working world, the state requires you to, especially if you're doing foam sheathing, that state's going to require you to show where you've got these brace wall panels on your plan. The other thing that's becoming a thing that wasn't a thing when I started is what's called portal frame or extended garage door headers. Because if you think about it, if the wind's coming from the left here, that's a weak point because I've got this big honking opening in that wall, and there's very little space to resist that wall wanting to tip over. So in some circumstances, the codes are requiring portal frame garage door headers where they actually extend the header out and then they put a metal strap on that, and then they put OSB from the bottom plates up to the top of the header, and that ties it together. And you can see that's a much stronger joint than just relying to that wimpy little connection where it's sitting on the shoulder studs at the header. Now, have you guys ever done portal frame garage doors headers? I'm seeing yes, and I'm seeing yes. So that is a real thing now out in the real world. That hadn't been invented when I started. We had all these big garage doors, and they're just held up by a couple studs. But when you look at this, the other thing that's getting bigger, if you looked at the capstone projects, garages are getting bigger. 4, 5, 6 car garages, big, huge double doors, big, huge garages for RVs. So this idea that you have to provide the stability left to right is important, or I should say shear strength when the wind blows on the side of your house. Okay, so this class starts at 9:30, so maybe we can get our Forte lesson in. So this is a little help for our Forte lesson and our assignment. Now, I'm not telling you about roof framing yet, but I'm going to tell about you in the future weeks. But for whatever reason, I did roof framing for my header assignment. And I just wanted to talk a little bit about how much load comes onto a header. So here's some trusses. And here's the outside wall. Let's imagine they're clear spanning across to the outside wall. What I'm saying at the gable side condition here, I'm telling you half the span of the roof goes onto that wall and on that header. Half goes on one side, half goes on the other side. And then you also have to take all this overhang load on one side and drop it onto that wall. So that kind of makes sense, doesn't it? Because there's no way that this overhang is going to get transferred over to the other wall because it's got a wall 3 feet away or 2 feet away. All of it's going to go into that wall that it's next to. So you basically divide the roof right down the middle. Half of it goes one way, half of it goes the other way. Now, if we've got a gable end, and imagine we've got a header in that gable end wall here, the way that typically it's framed, especially if you get a big enough gable overhang, a gable end overhang, is you have what's called a dropped gable end truss, and then you have 2x4 outlookers. And what those are for is they're kind of making it like a teeter-totter, right? Because otherwise, if it's just the plywood sticking out with some wood stuck underneath it and some big 300-pound carpenters out on a 2-foot gable end overhang, it's gonna be a problem. So we need to stabilize it. So what we do is we run these 2x4s back to bring that load back in and support that overhang. So all of that overhang load, so if that's 1 foot or 2 foot, all that overhang on the gable end comes down into my wall header. And then typically roofs are done at 2 foot on center. So worst case is going to be at 1 foot is coming down into that outside wall. Because if you look at this, all this 2x4 load and the overhangs coming into the outside wall, And then half of this 2 foot on center spacing is coming into the outside wall. So keep that in mind when we go ahead and we size our gable end trusses. So any questions? Let's move on to Forte. We've got 20 minutes before we've been here an hour, and I think we can get through our first Forte, our lesson, and then you can just work on assignments the rest of the class. So let's go ahead and get into Forte Web. If you want to find this on Blackboard electronically, I'll show you where that is. Let me close this out. Okay, so we're on structural concepts and we're on unit 3.1, wall framing and headers. That's the PowerPoint I just showed you. I'm going to hand out a hard copy for those of you that want to follow along in my script here, but this is the plan we're going to be using, which is up here. And if you want the electronic copy, that's where I just showed you. That's the electronic copy. So since I've printed these out, we did this last time. Them out for you. Exactly right. Okay, so we're going to do this script here. So let's go ahead and log ourselves into Forte Web. So I got to do my login here. And I got to remember my password. Okay, hopefully you all had the Forte Web bookmarked and you remembered your login. So I'm going to give you a couple seconds. So we're going to do a new file. And we're going to call it, I'm going to call mine 2026 wall header in class. Maybe I'll call it example just to separate it. And I've got my caps lock on. I'll quickly fix that. Okay, blue check box. So we are doing a one-story house that has 2 windows on it. And it looks like this. Its pitch is 5/12. It's got a 1-foot gable end overhang. It's got a 3-foot side overhang. Its dimensions are 20 feet by 40 feet. And there's my window size, 6 foot wide. And then this one is 3 foot wide. Okay. So it's a very simple house and it's a 1-story house. So let me just explain. When we get into Forte, so let's imagine this top part is just a 1-story house and it's on a basement. Where my hand is the basement. Say my floor load is 40 pounds per square foot live load and 15 dead load. Is any of that floor live load getting up to the header? No, absolutely not. There's no way for this floor load to get up to that header. Now, if I'm doing a header on the first floor of a 2-story house, I can have floor load coming down. Like say, here's a header right here on this one. I can have floor load coming down and roof load coming down on the same header. Now here's another condition where I've got a header above that doesn't line up with the header below. So I would have some roof load coming down on this part of the header. I'd have a uniform flow load coming down over the whole header. And then I'd have a point load, which is half of this roof load that hits this header coming down at a point onto my header. So I'm not That's like the advanced level, but once you understand how to use Forte, you can drop all the point loads and everything on, but I'm not gonna do that for this first assignment. It's gonna be very simple. It's just gonna be a one-story house with roof load coming down on it. Now, somebody asked about this model here. Before computers were invented, they made the students buy these kits, and then you got a bunch of balsa wood sticks, and then they have these little things called timber jacks, which are razor blades on a handle like a paper cutter like that. And you cut all your studs to length, and you put them together with these tiny little nails, pushing them through the balsa wood, and that's how they learn framing. Well, the problem is these cuts are well over $100 now. But people still do them, like a faculty member that taught in HVAC, he gave me this, because him and his kid did these for like fun, fun projects in the winter. So they still make these kits, but we don't use them anymore for teaching. But I guarantee you would probably learn framing really well if you had to cut all the studs and put them all together. Okay, so let's go ahead back to our assignment here. So we're going to rename our level for first floor, just like we did before. So we're going to click on the pencil. We're going to type in first floor. Hit the blue check box. Oh, let's go back and check our current code. So let's go back to job settings. Let's make sure we do the code version to IBC 2024. So I went back to wall header example. I clicked on job settings. Oh, let me do my mouse highlighter. I know you guys like that. Okay. Okay, so we got IBC, we're at first floor. That's all good. We'll keep all this what it is. Now what we're going to do is set up a wall header. So we're going to hit plus. And the beautiful thing is there's a picture. You don't even have to know how to read, but that is a wall header. So we're going to add that on there. And under member notes, we're going to type in, this is the 7'6" one at the sidewall. So that's what we're going to type in. So we're going to type in 7 feet dash 6 inches header at side wall. Now I'm going to switch back to all caps. Okay, so deflection criteria, we're going to keep it at code minimum. That looks pretty good. So now, as far as spans and supports, if you're looking at my script here, I copied the code. Headers and bearing walls should be supported in accordance with subdivision 1, 2, or 3. Headers 3 feet or less shall be directly supported. Well, we're not 3 feet and less. Headers greater than 3 feet, but less than or equal to 6 feet shall be directly supported each end by a single common stud and a shoulder stud. We're longer than 6 feet because our window is 7'6" long. So this is the one we need. Shall be directly supported on each end by a single common stud. That's the one that runs up past the header. That doesn't do anything to hold up the header. We were more concerned about the 2 shoulder studs. So there's 2 studs that this header is sitting on each side, and that's what we need to show on Forte. Because 2 studs are going to be 3 inches of bearing because the studs are 1.5 inches if they're 2x6s. Okay. So let me zoom in on this a little bit. If you're following your script, this is item number 8. We're going to set it up for the 7'6" rough opening width and the 2 shoulder stud bearing. So let's go ahead into Forte and set this up like that. So we're going to click on the green picture to show it. We're going to change our span to clear span because that's the rough opening where it's already at clear span, 7 feet 6. Click out of it. Our bearing length is going to be 3 inches on both sides because it's the 2 shoulder studs or 2 jack studs, however you want to call them. And it's going to be clear span. It's going to be bottom. It's going to be a trimmer. it's gonna be spruce pine fir. So I guess I don't have to change any of that. So I'm gonna just hold on a second. Your overall length should be 8 feet, 7'6", 3-inch bearing on each side, clear span, bottom, trimmer, spruce pine fir. Everybody cool with that? Okay, let's move on. So this is where we're gonna get screwed up if we're gonna get screwed up for, big time. Right there, where it says 1, the default tributary width is 1. If we do that, our header will fail. So what we're going to do is look at our floor plan. So I've got enough information on the floor plan to tell you what my tributary width is for this header. The header we're talking about is in the bottom wall here. It's that 7'6" wide window. How much tributary width do we have? I'm going to sit here until somebody raises their hand and tells me. Remember the last slide on my PowerPoint? Yeah. Let's zoom in so you can actually see it here. That would probably help you get a good answer. It's 20 feet and a 3-foot overhang. So can I get them?
It's gonna take half of it. Oh, yeah.
Okay, let's have somebody come up with a number and raise their hand. It's not 26. It's not 23.
13.
Yes. How did we get 13?
Plus the-
Half of the distance plus the overhang. Okay, get that in. So think about it. If we divide this roof directly in half, half of it's going to go to one wall, half of it's going to go to the other. One overhang on one side is going to go to that wall next to it, the other overhang on the other. So it's not rocket science, but you got to remember, don't overthink it, but you got to think logically about it. So each side is going to have a 13-foot tributary area. If I had a header on the top, that would also take 13. It's half of the span plus all of the overhang. Okay, so let's go back into Forte and we're going to change the 1 to a 13. And this is critical because if we leave that at 1, we're 1/13 of the load that's coming onto it by that one number. So that shows you garbage in, garbage out. So I'm using dead load of 15, even though code minimum is 12. I always did that in the real world. They put more layers of shingles on sometimes rather than tearing them off when they re-roof. So I always felt comfortable doing 15. Now we've got to do our roof slope because the more steep your roof is, the more shingles you got coming down in that 13-foot span, right? So if I got a roof that's almost vertical, I could have this huge amount of shingles that's only spanning like 13 feet. Whereas if it's laying flat, I've got the absolute bare amount of roofing on there. So we got to put our pitch in here. So all we have to do is hit 5 and then click out of it. It will assume. So what it's doing is it's adjusting that dead load based on the pitch. So I'm just going to change mine here. If I made that 14, which would be really steep. Oops, let's try it one more time. Why is it not doing it? Okay, so I did 12 to 12. So you see that adjusted dead load went way up, but we're not 12 to 12, we're 5 to 12. I guess they're thinking nobody does 14 over 12 pitches, but if you're doing a Gothic building, you might have one. I don't know. So anyway, this is the other mistake students make. It by default, Forte gives you a floor live load of 40 pounds per square foot. Great, but we don't have a floor on our header because it's a one-story header only opening up a roof, holding up a roof. This is my example here. If this is imagine this is my one-story house here, the top part here. My header's holding up the roof. There's a floor down there above my basement. Does that load ever have any chance of getting into that header? No, it doesn't. So we got to make the floor load 0. Now, the other thing you have to remember is we have a choice. We can either put our code required snow load in Wisconsin is 30 pounds per square foot. So typically Wisconsin roofs are designed for the worst case, which is the 30-pound in our southern part of the state snow load. So we're going to put that under snow. We're not going to put it under roof live. We're not going to put it under wind or seismic because that's what the code requires us to size for. Because Wisconsin roofs get most of their load in the winter when they're loaded up with wet, heavy snow. So we've got this at 30. We got rid of the floor load. We've got our roof load adjusted and we've got our dead load set to 15. And we absolutely have our tributary width set to 13 feet. Okay, so now we can skip the holes. We can skip the location analysis. We're going to go to product selection. So like I said before, habitat typically, well, this is like pretending this is a habitat house. Now the assignment's going to be different, but this one we're going to do it like we do for habitat, which is two 2x12s SPF, and they only use LVLs if 2x12s won't work. So again, just for this example, we're going to pick commodity lumber because that's what your normal 2x12s are. And we're going to find 2x spruce pine fir number 1 or 2. So that's right here. And we're going to use a 2x12, which is 11 1/4, because that's what Habitat tells us they want to use. And like I was talking before, even though a 1-ply would work, it's standard to always use 2-ply. So we're going to use a 2-ply. And then we've got standard orientation. It's not like a diving board where the 2x12s are laying flat. They're up and down. So then we do the solutions. And we said only show solutions that pass design. Since we only had one, that's fine, but I always like to get in the habit of looking at that. Now, they are trying to sell timber strand. Remember on the floor beams, they tried to sell us timber strand. Now they're trying to sell us more timber strand for headers, which is basically really thick OSB. And they're saying that you can get by with only 1-ply of 1 1/4 inch timber strand OSB at 11 7/8, and it's going to cost a lot less money. So I think they make a really good profit on timber strand because they're trying to sell it on everything, even if we don't ask for it. And then here's where we get our report. We're going to still highlight the 2x12s. So you can see the percentage of load we're using. It's a little overkill probably structurally, but that's just the way we typically roll. We just typically put 2x12s everywhere for habitat. And then if we want to go ahead and make our PDF to turn that in on the assignment, we click there. So let's go ahead and do the last one on the gable end, and then we'll take a break, and then I'll show you your assignment. Or maybe I'll show you your assignment, and then we can take a break. Okay, so let's go ahead and we'll do a new header. We're going to click on Add Member. We're going to pick on a wall header again. We're going to keep this all the same, except we're going to type in gable end header here. Now by code, we only need the 1 shoulder stud. So we're only going to have 1.5 inches on each side. So let's go back and look at our drawing here. What's our span of our rough opening? It's 3 foot wide. So let's go back into Forte Web and we're going to keep it at clear span. We're going to type in 3. And we're going to keep the bearing length at 1.5 inches because again, by code, we don't need to do more than that. Bottom trimmer, spruce pine fir. I don't have to change any of that. So you can see this goes pretty fast. We got to get our loads down right. So let's look at our tributary width here. I'm going to ask, now you can look at the script and tell me what the loading is, but I'm going to ask you to tell me what the load is on this gable end header as far as our tributary width. I got a 1 foot overhang, so it's 1 foot plus what? 1 foot, because roofs are typically 2 foot on center. So these little outlookers are going back 2 feet here. They're sticking out 1 foot past the wall and they're going back 2 feet. So half of that 2 foot space goes back to the next truss and half of it comes onto our header here. So this is only going to have a 2 foot tributary width. So let's go into Forte Web and do our tributary width at 2 feet. Our roof's bed load's still gonna be 15, just like before. Our roof slope's still gonna be 5, just like before. We're gonna get rid of the floor live load. And we're gonna do a 30-pound snow load. We skip holes and location analysis. So your overall length should be 3'3" because it's only going down on a single shoulder stud on each side. I always go to product selection, same as before. Commodity lumber, 2x spruce pine fir, number 1, number 2. 2-ply. This is gonna be way oversized, but this is the way Habitat rolls in the real world. They do 2x12s no matter what, standard. Solutions. So if we were doing advanced framing, we could theoretically get by with a 1.5-inch timber strand, only 3.5 inches deep, and have lots more room for insulation in that wall. But I'm just telling you, traditionally, that's not the way the real world works. How did you guys frame them in the real world? Did you always put two-ply headers everywhere when you were on wood tech? Yeah, so that's just the way it is. So you can argue with Josh whether that's the real world is wrong, and he's probably going to tell you it is, but the real world is a lot of times size worst case, always do two buys, and you don't size each header individually.
The two headers together and connect to the outside.
Oh, so he did this the way my structural engineer wants to do it. Okay,
These,
okay. Okay, so there's our report. That is your lesson. Now, let's show you the assignment. Now, I want you to do the assignment in a new file. So don't just add more headers onto this wall header example file. But let me show you the assignment, then I'm going to give you a break, and then you can work on this assignment while it's still fresh, and then you can also work on your floor framing if you want. So let's go back in. So I've given you the same thing for the assignment. Here's the drawing we're using. So let me close off my lesson so I don't get confused. So I'm giving you a floor plan, and the headers are either going to have a letter or a number. So the windows have a number in this case, and the doors have a letter. So if I say I want you to size the header over door C, that would be the garage door. If I say I want you to design the header over window 2, that's one of these 10-foot span headers. The garage door is a 16'3". So you've got all the dimensions you need for your span. You've got the dimensions you also need for the width of the house, because these, as you can see on the framing plan, the trusses are spanning outside wall to outside wall. Now, what you need to get on the framing part of it, oh, how do I get over there? Here we go. The typical gable end overhang is only 1'6". And the eaves overhang is 3 foot. So those are the two numbers you need for your overhang. But then all the other dimensions are up on this plan. Okay, so you're going to need to have that out when you look at it. The other thing you need to look at is, I'm going to just open Forte header sizing in a bigger document for you to look at. This is the actual assignment. So that drawing is from your employer. We're going to use the code to the 2024 IBC. We're going to do a 612 roof pitch. So it's different than the 512 on the example. You're going to have to type that in properly. We are going to do all our headers out of LVL in this case, but we're going to do a 2-ply LVL. I'm just doing it just for the heck of it to have you size with LVLs instead of with 2-bys. So all headers should be 3 inches to 3.5 inches wide. That way it's going to be, they can fit in a 2x4 stud garage wall, and they can be insulated in a 2x6 stud house wall. So what does that mean? 2-ply, and we're using LVLs. LVLs are how wide? They're not 1.5. I'll give you a hint because they're made out of engineered lumber. What are LVLs or microlams typically wide? 1 3/4. Okay, so 2 of them is 3.5 inches. So you're going to use a 2-ply header is basically what I'm telling you. The garage door header cannot be deeper than 28 inches. All other headers cannot be deeper than 11.5 inches. All headers to be made of LVL. The roof snow live load is 30 pounds per square foot for Wisconsin building code. The dead load I'm using is 15 pounds per square foot. Now I'm giving you a little bit of, I'm not doing this to confuse you, but I just want you to remember that we take the 40 PSF out. I'm telling you the 40 PSF, this house has a 40 PSF floor live load, but then I'm also telling you this is a 1-story house, so no floor loads on the wall headers. I want you to get that out of there. Same thing with the floor dead load. There's no floor load on the wall headers. This is just a 1-story house. The opening dimensions on the drawing are for the rough opening, so you can use those window dimensions exactly and plug them into Forte. So the amount of shoulder studs at each each header are as required by the Uniform Dwelling Code. So if we're less than and equal to 6-foot rough opening, we're going to have the 1 shoulder stud on each side. If we're greater than 6 foot, we're going to have 2 shoulder studs on the both side. So pick the stud header with the lowest cost index that satisfies all the criteria above. So I'm telling you they have to be LVL, so we're not going to use their stupid timber strand, even if it's cheaper. So I want you to give me 4 PDF member reports up to Blackboard for each header. So there's one for the garage door opening, there's one for window 2, there's one for window 3, and there's one for door B. So let's just show you where these all are on the plan. Garage door headers there. Window 2 is there. Let's zoom in some more so we can see it. That's window 2. This is door B. And this big honking one in the gable end is window 3. So you're going to design 4 headers. You saw how long it took us to do 2, right? It was pretty darn fast. So you should be able to get this done in plenty of time. Most times students end up leaving early. But if you, in your case, if you want to do or check over your floor framing assignment, I'm giving you enough time to do that. Now I've had you in class for an hour and 10 minutes, so well over the time for taking a break. So go ahead and take a break if you want, but that's all I got for my lesson for today.